Hello, students. We take a look at some more infinite series. Specifically, we are going to now look at specific examples of geometric series. Let's recall our theorem for the convergence or divergence of a geometric series. Given any geometric series, a and r are real numbers, a is not equal to 0, we know that the series will converge if the absolute value of r is less than 1, and if that's the case, the sum of that infinite series is a over 1 minus r. The geometric series will diverge if the absolute value of r is greater than or equal to 1. It's a really neat theorem. It's very quick and easy to use. The whole clincher here is, though, we have to start with a geometric series. So it's all about recognizing the pattern and then determining what a and r are in order to determine if the series converges or diverges. So let's take a look at a couple examples. Example 1. Determine whether the following geometric series converges or diverges. If it converges, determine its sum. All right. So the key with determining the convergence or divergence of a geometric series is actually finding the r value. So let's start by writing out our geometric series and expanding it and seeing if we can't figure out what r is going to be. So we have the geometric series from n equals 0 to infinity of 5 to the n plus 1 over 2 to the n. Now remember, geometric series satisfies that certain pattern, right? A plus A times R plus A times R squared plus all the way, right? So our job is to figure out what R is. Personally, I'm a very visual person, so I'm going to list out the first couple terms of this series. Specifically, we want to pay attention to the index. On an infinite series, this index can change. In this particular case, n is 0. I don't know if you remember, but if you looked back on your theorems, in that case, n was always 1. Well, I'm not going to let that bother me. I'm simply going to say, okay, well, we're going to start by n being 0, and then my next term is going to be n equal 1, and my next term is going to be n equal 2, etc., etc., etc. So I'm just going to go ahead and I'm going to list out my first couple terms. So when n is 0, the first term in this infinite series is 5 over 0 plus 1 over 2 to the 0th power. The second term is 5 over 1 plus 1, 2 to the first power. The third one is going to be 5 over 2 plus 1 over 2 to the second power, etc. Do you see the pattern? I'll put one more in there. So that's 5 over 3 plus 1, 2 to the third power. So this is our pattern. This is our geometric series. Now let's do a little simplifying. 5 to the first is just 5, and 2 to the 0th is 1. So the first term is 5 over 1. The second term is 5 to the second over 2 to the first. So I'm actually going to do it like this. I'm going to write something out. 5 to the second, right? 5 to the 2, because 1 plus 1 is 2. So this is just 2 up here. So 5 to the 2, I'm actually going to list out as 5 times 5 over 2. Why do I do that? Again, I'm an extremely visual person. So on the third one, I'm going to write out, let's see, this is the third power, right? 5 to the third. So really, this is just 5 times 5 times 5 over 2 times 2, right? 2 to the second. Now, why do I list it out that way? Let's take a look. Remember, we're looking for our A values and we're looking for our R values. And I just find it easier that if I list things out, I can visualize and see them. So A, remember, in a geometric series is our first value. So A is 5. And if A is 5, then R becomes that ratio or that number that I'm multiplying by the first to get the second. So what would R have to be? R has to be the number that I multiply by 5 over 1 to get 5 times 5 over 2. It looks like my ratio or my R value is going to be 5 over 2. Because if I take 5 over 2 times 5, that's going to give me that term. And that kind of looks good, right? Check this out. What would I need to get the next pattern? Well, I have a 5 times a 5 over 2. What do I need? I need the same thing, right? So again, each one, I'm multiplying by an additional 5 over 2, and that's what's giving me my next term. So R is 5 over 2. A is 5. Do you guys see that? And so A is 5. R is 5 over 2. You might find it a different way. That's fine. But this is one way to find the ratio that you're multiplying by. And how do I tell if the series converges or diverges? I look at which value? I look at R. And what do I know about R? R is 5 over 2. How is that in reference to the number 1? Well, 5 over 2 is actually bigger than 1. So if 5 over 2 is bigger than 1, you can look back at your theorem. The theorem says that if R, the absolute value of R is greater than 1, what happens? My series does what? My series diverges. And since 5 over 2 is greater than 1, this means that this geometric series diverges. Let's summarize that. The geometric series diverges. Geometric series diverges because R equals 5/2, which is greater than 1. End. Done. That's pretty simple. The key with geometric series, now that we've done all the hard work to develop the theorem, is to simply find the A and the R value. So let's take a look at the next example. All right, let's do example 2. Determine whether the following geometric series converges or diverges, and if it converges, determine its sum. This is the infinite series n equals 2 to infinity of -1 to the n times 7 over 3 to the n. I like to look at these series and I like to expand them. I like to look at the expansion or the summation written out so that I can take a look and find what A and R are. So I'm going to write out my infinite summation n equals 2 to infinity of -1 to the n times 7 over 3 to the n. I'm going to pay particular attention to my index. Notice I'm starting at n equal 2. So when I go to write out this infinite summation, I'm going to start by letting n being 2. So my first term is going to be when n is 2. And then the next term is going to be when n is 3. And then the next term is going to be when n is 4. That's enough to get a pattern. So I'm going to take -1 to the second times 7 over 3 to the second. I'm going to take -1 to the third times 7 over 3 to the third. And then -1 to the fourth times 7 over 3 to the fourth. So it's all about the pattern. And often students are faster than me sometimes getting these, but here we go. Let's see. So we've got -1 squared, which is 1 times, so that's 1 times 7 over 9. I'm just going to write it out right here. And then it's going to be -1 times 7 over 27. And then it's going to be 1 times 7 over 81. All right, so what's this pattern? What's our A value? Our A value is our first term, right? And so it looks to me like the first term is just 7/9. So it looks to me like A is 7/9. Now what's R? R is the number that I multiply by the first term to get the second term. Well, I know I'm going to have to multiply by a -1 because I'm going from a positive to a negative, right? But what else am I going to have to multiply by 7/9 to get me 7 over 27? I think I'm multiplying by 1/3. In other words, it looks to me like R is -1/3 for this example. If I go here, I take 7 over 27, and again, I have to multiply by a negative because I go from a negative to a positive, so I do have to have the negative. And again, if I multiply by 1/3, yep, gives me 81 on the bottom, right? So its R value is negative 1/3. Now you can also get that if you manipulate. You can also get that if you manipulate up here at the very beginning and look at -1 and 3 and see how they're both in the power of n in that expansion there. But I like to write it out. I just do. It gives me A and gives me R. So however you get it is perfect. But once you get your R value, then we apply our theorem, right? So we take a look at our R value. Our R value is negative 1/3. And what's the theorem say? The absolute value of negative 1/3, we take its absolute value, and that is equal to positive 1/3. And that number is less than 1. And what does that tell us? If our R value is less than 1, what does that say about our series? If our R value is less than 1, then our series converges. Yay. So that means our series converges. Moreover, it tells us that we converge to a sum, and that sum of the infinite series is A over 1 minus R. So let's actually get our sum here before we write our conclusion. So we know that the series converges because the R value has an absolute value which is less than 1. We know that it converges to the sum of A, which is 7/9, over 1 minus R, which is negative 1/3. Just be careful here. We got that negative in the bottom. So that means I have 7/9 over 1 plus 1/3, which is 7/9 over, I'll just go ahead and put all the fractions out because I know fractions are our favorite friend, right? So this is 7/9 over 4/3. And what do we do when we have a fraction on top of fraction? I'm going to go through this like super fast, but we flip and multiply. And so what does this give us? This tells us that we have the sum equal to, and I'll do one little cancel here because I see that 3 goes into 3 and 3 goes into 9. So I'll just do my reduction. That tells me that the sum is equal to 7 over 12, if I've done my math correctly. So let's write our statement. This geometric series, so the geometric series converges. And we know it converges because its R value, because R equals negative 1/3, and the absolute value of negative 1/3 is less than 1. When that's the case, then this series converges. Moreover, the series converges, or the series has the sum, I'll just write the series converges to the sum of 7/12. Or if you like, you could write the sum of the series is 7/12. That works just as well. Okay. Let's move on to our last example. Example 3. Determine whether the following geometric series converges or diverges. If it converges, determine its sum. I want the infinite series n equals 1 to infinity of 2 times 5 over 8 to the nth power. Let's write that out. N equals 1 to infinity of 2 times 5 over 8 to the n. Now, if you're all about recognizing patterns, you see we're kind of set up right now to actually pull off the A and the R value because this kind of matches our pattern. I don't know if you remember, the pattern is n equals 1 to infinity of A, R to the n minus 1. We can kind of manipulate it and kind of make it look like that pattern if we want to. But again, I'm one of those people that just likes to list things out. I like to do it where I visualize everything. So I'm going to start with my index being 1, and I'm going to let n equal 1, and then I'm going to let n equal 2 and n equal 3. I'm going to list out the first 3 terms in my series. So that's 2 times 5 over 8 to the first power, and 2 times 5 over 8 to the second power, and 2 times 5 over 8 to the third power, And so listing these terms out, it kind of helps me to find what my A value is going to be. In fact, we can just pull off our A value, can't we? Let's take a look, right? Oh, hang on one more second. Let me just be a little more rigorous here. This infinite series does go forever. We just got the first 3 terms to get the pattern. So what is my A value? My A value comes from my first term. So A is actually 2 times 5 over 8, or if I like, that's actually 10 over 8, which reduces if I want to 5/4, but that's my A value. What about my R value? What am I having to multiply by the first term to get the second term? What am I having to multiply by the first term to get the second term? What number? Well, I have 2 5/8. What's changing over here is I have another 5/8, right? I have 2 of them over here. Doesn't it look like R is now 5/8? So I have 2 of them here, and then what do I do to get to the next one? Now I have to get 3 of them, and that's what happens when I multiply 2 times 5/8 to the second times another 5/8, right? Gives me 5/8 to the third. It looks clear to me that our R value is 5/8. That's what we're looking for. We can now go on and talk about the statement of convergence or divergence. Our R value tells us whether the series converges or diverges. Our R value is 5/8, and 5/8 is less than 1. And what happens from our theorem is this: if the absolute value of R is less than 1, then that means our series converges, right? So that means that this infinite series is going to be converging. Moreover, it tells us that the sum of this infinite series is A over 1 minus R. And so let's actually go ahead and calculate our sum. Our sum is A. A is 5/4 over 1 minus R, which is 5/8. So again, now we have a little bit of fractions to do, but we've got 5/4 over 3/8. And flip and multiply, right? Cancel as we go. And so what does that tell us? That tells us that the sum of this series is actually 10 over 3. So let's summarize and write down what we know. The geometric series converges. And how do we know it converges? It converges because our R value is equal to 5/2, and 5/2 is less than 1. Moreover, the sum of the geometric series is 10 over 3, 10/3. This is an S, not a 5, okay? So the sum of the geometric series is 10 over 3. So that completes our discussion of infinite geometric series. The key being find the R value and compare it to the number 1.